Okay, good. Good morning. So today what we'll do is we'll continue working on chapter 6. So we were looking at what's called the Bohr model. And the kind of standard problem that you see in the Bohr model topic is this idea that you have, this is for hydrogen, you have these different levels. And remember, the energies of these levels get closer and closer and closer to each other. And we number them with whole numbers, 3, 4, 5, 6, so forth and so on, right? So vertically, it's increasing in energy. So the energy of the second level is greater than the energy of the first. And come back to the kind of physical picture of how we're viewing this. The nucleus is at the center. There's an electron in this orbit or this state, and that electron can be promoted. It can be sent up. It can jump up to a different level. So this is 1, this is 2, this is 3, this is 4, this is 5, so forth and so on. So it can undergo a transition from one level to another. Okay. The most stable form of hydrogen is the case where the electron is in the first level, which we call the ground state, right? So this one down here is called the ground state. That's the most stable state. So we can represent the electron with a little arrow. And we'll see how we do that a little bit later more, where that arrow comes, that notation for the arrow comes from. But the most stable form is where it's in the n equals 1. But if you heat the atoms up, if you have a collection of hydrogen atoms and they're bouncing around and they're really hot, like at thousands of degrees, which is pretty high temperatures, but a traditional light bulb reaches those temperatures. The filament in an old light bulb can reach thousands of degrees. At that temperature, some of the hydrogen atoms, the electron won't be in the first level, it'll actually be in the second or third or fourth level. So it can be in any of these levels. So some of them will be up here. And so if they're up there, they can undergo a transition down to the first level. So they can go from 4 to 1, for example. And we had notations for that, right? We would say n equals 4 goes to n equals 1. When that transition occurs, when the electron jumps from the fourth level down to the first, so that would be like from here to here, okay? When that happens, a photon is emitted, right? So that transition results in the formation, the creation of a photon. And remember, the photon is an electromagnetic wave, so it's a little wave packet. It has a wavelength and a frequency, and it moves at the speed of light, which is 2.9979 times 10 to the 8th meters per second. So when the electron jumps down, this photon just goes flying out into space, and that's called emission. All right. So the standard problem for this topic is they tell you the transition. They say it's going from, let's say, the fourth level down to the second level, and they ask you what wavelength the photon will have, right? So the idea is when the electron jumps down, the difference in energy between those two levels is going to be equal to the energy of the photon. And so then you can convert energy of a photon to the wavelength of the photon. And then it's just a matter of getting the units right. Okay, so let me show you what I mean by that. So let's say, for example, you know, in a hydrogen atom, again, this is only for a hydrogen atom. The electron transitions from n equals, let's do 6 to n equals 1. Calculate the wavelength of the photon emitted. Okay. And there's an equation that they give you. They say that you calculate the energy of the electron. So N meaning what level it's in, but that's the energy of the electron in the atom is equal to minus R divided by N squared. And then the N are these levels, right? 1, 2, 3, 4, 5. So the logic of this is that if you want to find the difference in energy between those two levels, you do minus R over N squared, where you're doing the final value of N, right? The final value, minus R over N initial squared. N final minus N initial. So let me actually just go ahead and put these in parentheses. So there's a lot of negatives in here, right? The negatives are in there because there's a negative in the formula, right? This formula has a negative. But this other negative, this one in between here, is there because delta E is E final minus E initial. Okay, so that's why there's 3 negatives in there. Now, you can do a little bit of algebra that might help you out. Yeah, that's squared. That might help you out a little bit here. So one of the things you can do is you can say, you know, when you're subtracting a negative, that's like adding a positive. So you can write this as minus R over N final squared plus R over N initial squared, right? That should work. Right? All I've done is I've taken minus and minuses plus, but there's a couple other things you could do. You know, typically if you have a negative, let's say I had negative X plus Y, we could also write that as Y minus X, right? So if you have negative R over N squared plus R over N squared, you take the second term and write that first and then just write it minus the first term. So we could also write this as R over N initial squared minus R over N final squared. So you could do that too. I mean, it doesn't matter which form you use. And then there's one more step you could do. You could say, wait a minute, both of them have an R, so I could just factor out the R. And I could write it as R, and now I factored out this R up here. So this, when you take out the R, it's just a 1. So it's just 1 over N initial squared. And then I'm taking out the R on the second term, so 1 over N final squared. And that'll give you delta E also, right? So that works too. So you have different forms you can use. And if you look at the literature, meaning textbooks and the internet and all that, you're going to see all kinds of different forms of this equation, but they're all kind of based on the idea that you got a constant. Oh, and there's one thing I should say, you know, I didn't even think about it. This is not the gas constant, right? So Alex, they put a Y in there. So I'm going to put the Y in there also, because we shouldn't get that confused with the gas constant, right? We're using a similar symbol, it's R, but this is RY. So RY is not the same as 8.314 or 0.08206, okay? So here we go. So suppose we're saying we're going to go from 6 to 1, right? 6 to 1. So if you're going from something, so N equals 6, 2 N equals 1. Where you're coming from is the initial. So this is N initial. And where you're going to is N final. Okay. So now let's go ahead and just put these numbers in. We're going to get R sub Y times 1 over 6 squared, right? N initial is 6, so 1 over 6 squared minus 1 over 1 squared. Okay. All right. Well, now you just do the arithmetic inside the parentheses. It's really 1 over 36 minus 1 over 1. 1 over 1 is 36 over 36. So you can either do it on your calculator or you can just do 1 over 36 minus 36 over 36, and you get R sub Y times minus 35 over 36. Okay, or you'll just get a decimal number. If you want to just use a decimal number, that's perfectly fine. Okay, so now let's come back to what R sub Y is. R sub Y is equal to 2.17. Okay, I have to look it up because I don't remember all the sig figs in it. So let me see what it is. It's 2.17987 times 10 to the minus 18 joules. Okay, so now we've got our Y. So let's go ahead. I'm going to create a new slide. So now we've got delta E is equal to 987 times 10 to the minus 18 joules times, remember it's negative 35 over 36. So then we just need to go through that calculation. So let's see what that works out to be. 2.17987 times 10 to the minus 18 times 35 over 36. And you get negative 2.11932 times 10 to the minus 18 joules. So notice there's a negative, right? That negative came from the negative that was there, because when you take 1 over 36 and you subtract 1, you get a negative number, right? So that negative is there. And I just want to make sure that you understand the interpretation of that negative. Negative has meaning in this context. Negative means the energy was reduced. So the idea here is that the electron started in the 6th level and it jumped down to the 1st, so it lost energy. Okay, if it loses energy, that energy has to go somewhere. It goes out in the form of the photon, right? You can almost think of it like an exothermic process. In a sense, emission is exothermic, right? So it's releasing the energy from the atom. And so that's why it's negative, okay? Now, that's the difference.
I'm so sorry, Professor. May I ask you, where did you get minus 35 from? I'm so sorry, I didn't get it.
So what I had was 1 over 6 squared minus 1 over 1 squared, right? So that's equal to 1 over 36 minus 1 over 1, right? 1 squared is 1. But you can write 1 over 1, if you want to have it in 36s, you can write that as 1 over 36 minus 36 over 36, right? 1 over 1 is 36 over 36. So that way the denominators are the same. So now you can just, this is just 1 minus 36 over 36. So that's minus 35 over 36. So that's where that came from.
Thank you, Professor.
Mm-hmm. So now that's the energy change for the atom, but we want to know about the photon, right? We want to know something about this photon that's flying out of the atom. So how do we deal with that? What we do is we say, hey, the energy of a photon is equal to either HF, right? Planck's constant times the frequency. So that was back in section 2. Or you can use this one, HC over lambda. Both of those equations are equivalent, right? This second one over here is just, it's just C over lambda equals F. We had that earlier equation, C equals lambda times F. So that means that F is equal to C over lambda. So I just substituted that in right there. So either one, but we want to know, the question is, what's the wavelength? So if they're asking for the wavelength, it's probably best to use this one right here. So now E of the photon equals hc over lambda. We know what the energy of the photon is. The energy of the photon is the same energy that the atom lost. Okay, so we know this is 2.11932 times 10 to the minus 18 joules. That's going to be equal to hc over lambda. Okay, you don't need the negative in here. The negative is how much energy the atom lost. The photon gained that much energy, so that's going to be a positive value. Okay, and then we're just going to rearrange this equation to find lambda. So let me write it this way. If we multiply both sides by lambda, I'm going to put E in parentheses there, multiply by lambda, that'll equal hc, right? Because if you multiply both sides by lambda, the lambda cancels out on the right side. And then we're going to divide both sides by E. So lambda would be hc over your 2.11932 times 10 to the minus 18 joules. Okay, hc over E, right? So if you start with this one and you're trying to find lambda, you should end up with hc over E. Okay, now hc is 6.626 times 10 to the minus 34 joules times 2.9979 times 10 to the 8th meters per second, right? So there's your HC. Those are the two constants that we've learned so far. Actually, there's three now, right? The third constant is this one right here, the Rydberg constant. So now we got three constants. 2.11932 times 10 to the minus 18 joules. Dimensional analysis, joules cancel, and your seconds cancel also. So joules times seconds, seconds cancel. So you're just going to get meters. Okay, now you just got to make sure you're good with your calculator doing scientific notation. 6.626 times, 6.626 times 10 to the minus 34, that's H, times 2.9979 times 10 to the 8, that's C. That's going to give you a really, really, really small number, 10 to the minus 25. Okay, but now we're going to divide it by this energy. So we're going to divide it by 2.11932 times 10 to the minus 18. And so what you get, let me just multiply this one more, times 1E9. Okay, what you get is 9.3729 times 10 to the minus 7 meters. I already put meters there, so let me erase that one. Okay, so you get this really, really small wavelength. Okay, now this is where you got to be careful. Some questions, they may ask you to put the wavelength, not in meters, but they might ask it for nanometers or micrometers or millimeters. So not always though, just sometimes they do that. So looking at this, this particular one, they don't. They just say calculate the wavelength. But suppose that they do. Suppose they say, we want to have this wavelength in nanometers. Okay. So what I'm going to do, let me save this one, is I'm going to 372. Oh yeah, I got it right here. So what I'm going to do is I'm going to say, hey, lambda equals 9.37286 times 10 to the minus 7 meters. And I'm going to pick a prefix just to show you. I'm going to pick nanometers. So let's say we want to convert to nanometers. Okay, that would be NM for nanometers. Okay. NM is also used for nautical miles, but we're not doing nautical miles in the chemistry class. Okay, so now here's how we do it. 1 nanometer is 1 times 10 to the minus 9 meters, right? Nano's 10 to the minus 9. So 1 nanometer is 1 times 10 to the minus 9 meters. So if we want to convert it to nanometers, this one here is going to be in the top, and this one's going to be in the bottom. So wavelength then would be 9.37286 times 10 to the minus 7 meters. And then 1 nanometer is 1 times 10 to the minus 9 meters. And there you go. Okay. So what you get out of that is 93.7286 nanometers. I would probably round that. 773 maybe nanometers. Okay. Yeah, 93, around 94, close to 94. Okay. So that's if they ask you to convert it to a different prefix. Like obviously, if they said micrometers, you would do 10 to the minus 6 instead of 10 to the minus 9. But nanometers is useful, and here's why. I just want to kind of reiterate this whole idea. When you look at visible light, remember, visible light is that little sliver of the electromagnetic spectrum. And generally, although there's no exact cutoff, generally we think of visible light as going from 400 nanometers to 700 nanometers. And then we had all the different colors, right? There was red, there was orange, there was yellow, there was green, there was blue, indigo, and violet. So reading from right to left, we would read that as Roy G. Biv, right? Roy G. Biv are all the colors of the visible spectrum, okay? And so red is the region closer to 700, and violet is the region closer to 400. And once you get below 400, once you go from about 400 down to about 10 nanometers, this is called ultraviolet, UV, right? So think about it. UV is next to V, right? Ultraviolet is just more than violet, right? So ultraviolet is right next to violet. On the other end, if you go beyond 700 nanometers, then you get infrared, which means less than red. So it goes, the order goes red, then infrared. So if it had been 710 nanometers or 750 nanometers or 1,000 nanometers, you would be in the infrared region. So that's why nanometers are kind of useful. When you see this, oh, it's around 90 nanometers, that tells you right there it's going to be in the ultraviolet range. So it's not something you could see with your eyes, but it is something that your skin would detect because it would probably give you a pretty bad sunburn if you were exposed to a lot of ultraviolet radiation, okay? So ultraviolet, Roy G. Biv, and then IR. And so what that tells us is that for the hydrogen atom, if your final is n equals 1, and your initial is greater than 1, 2, 3, 4, 5, 6, 7, right? What happens is it emits a photon that is ultraviolet. Okay, you can do the calculation. If you do, even if you do like 2 to 1, you'll get ultraviolet. 3 to 1 is ultraviolet. 4 to 1. Anything that where the final value is 1, it's ultraviolet. Visible, so let me write that here. So n final equals 1. Anything in the visible is n final equals 2. So if the final value is a 2, you get visible light. So when you do these problems, if you like do a problem and you see it goes like, oh, 6 to 2 or something like that, or 5 to 2, check it. Look, see if it's between 400 and 700 nanometers. It should be. And then if n final equals 3, that's where you get infrared. Okay, so infrared is where the final value is of 3. And you can have transitions where the final value is 4 and as well, but generally the ones that people are most concerned with are final is 1, final is 2, final is 3. And there you go. So that's the Bohr model. Now, before I go on to the more kind of modern quantum, I want to talk a little bit about the significance of the Bohr model, just real briefly. So what's significant about the Bohr model is that it's really the first theory of the atom that involves what we would call quantum levels or quantum states. So remember, the electron is either in the first level or the second level or the third level or the fourth level. It's in one of those levels, right? But Bohr was essentially claiming that these are the only allowed states for the electron. The electron can't be in between these. That's not allowed. It can't be in between 1 and 2. It can't be in between 2 and 3. It can't be in between 3 and 4. That's not allowed. It has to be in one of these levels. And that's the only way that, or I shouldn't say that's the only way. That is the way that he described the idea that when you look at the light that comes off of an atom that's hot and it's glowing, you get specific lines, right? It's called a line spectrum. So you might have 410 nanometers, 434 nanometers, 486 nanometers, and 656 nanometers. Those are called lines. Those are the colors that are coming off of the hydrogen atoms. If you use a different element like helium or lithium, you still get these lines. They have different wavelengths and there's different numbers of them, but you might have 6 lines as opposed to 4, but they all have lines. So that means that in some sense, the atoms are quantized, meaning that the electron has to be in some kind of level that is discrete, meaning it's got to be 1 or 2 or 3. You can't have an infinite number in between. You can't have, an infinite number of possibilities in here. It's got to be quantized. And so that's the significance of the Bohr model. He was able, using his formulas, to calculate the specific wavelengths very, very well. We can measure them and get the same answers he got. But what he wasn't able to do is he wasn't able to explain why these particular orbits, why these states are stable, like what makes them stable. There's no real reason that you can see that one level would be more stable than another. There's nothing in the theory that explains that. So what happened was it took a different theory to describe why these levels might exist. And so let me talk a little bit about the next topic, which is called, this is 6.4. It's called the wave properties of matter. And in a sense, this leads us into modern chemistry. Of matter. Okay, and so the problem that you're going to do in this topic is called, understanding the meaning of the de Broglie wavelength. Okay, so let's talk a little bit about the de Broglie wavelength, what the meaning of that is, and then we'll look at an example calculation here. So the de Broglie wavelength is based on the idea that de Broglie had, which was this. We know that light is a disturbance of electromagnetism, right? So, if you have a light bulb, we know that electricity is what causes the light to be emitted, right? Light is emitted from a light bulb because you put electricity in it. So it must be some kind of electrical behavior. And what we know is that it is, in fact, an electrical behavior. It's also a magnetic behavior. It's electromagnetic in nature. So that means the electron must be important in terms of thinking about what light is, at least connected to it. So once you start looking at light, what you find is that one of the aspects of light is that it has certain behaviors that lead you to conclude that it's a wave, right? That, there's a famous experiment called the double slit experiment that involves what's called diffraction and interference. And I'm not going to go through all of that. They teach it much better in a physics course, but essentially there are properties of waves that light has, okay? But Einstein showed that, in fact, when you start studying light, you can also show that it behaves like a particle. So light is also behaving like little particles. Okay, in fact, it is now understood that if you really train your eyes in a very, very dark room, a specially made room, you can guess whether a machine's, here's the experiment. Essentially what you do is you take a little laser, not a laser, but a little light source, and you send in 1 photon of light. And then you're in a dark room and it's shining right at your eyes. And then you can send 1 photon at a time. And what happens is they have you just push a button whether you think that a photon was shot at you. So if you think, oh yeah, I saw a pulse of light, you hit the button, right? And so what they do is they just send these photons 1 at a time and have you record it and record it and record it. And what you find is that some people can predict, yes, a photon was fired at me more than 50% of the time, right? More than half the time. In other words, better than guessing. So that suggests that they're actually able to perceive, not every time, but more than 50% of the time, they're able to perceive whether a photon was fired at them or not. So that means that our eyes are so sensitive, they can, on occasion, detect 1 photon of light, okay? And that photon has a certain amount of energy, and of course, the photon has a wavelength and a frequency. So that means that light has 2 properties that are different from one another. In one sense, it's a wave, but in another sense, it's actually a particle. So we call this phenomenon wave particle duality. Duality meaning that it's both, right? It exists as both, depending on the circumstances. So under some circumstances, it behaves like a wave. In other circumstances, it behaves like a particle, okay? Now, what de Broglie said was, imagine if subatomic particles were the same way. Imagine if electrons or protons were not just particles, but they were also waves. So maybe they exhibit this wave-particle duality. And initially what people said was, that's ridiculous. You know, we can measure the particle nature of an electron. You have a Geiger tube, right? A Geiger tube, which they've had for 100 years now, it can actually detect individual particles of electrons. So it's clearly a particle. So unless you can show that there's some kind of experiment that shows the electron behaves like a wave, then we would just reject that. So initially it was rejected. But what happened was, these guys around 10 years after he came up with his theory, or 5 years, what they did was they did a very clever experiment. What they did was what's called a double slit experiment. And so what they did was they said, hey, we're going to let the electron have essentially a choice. So this is a detector back here, a detector plate. In those days, they used photographic film. So they did it in a dark room and they had a photographic film. And then these little openings, these are called slits. These little orifices are slits. So what they did was they just had a little gun that shoots electrons. So boom, 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 boom. Now, you may not know what the path of the electron is, right? So maybe it's going straight, maybe it's coming off this way, maybe it's coming off this way. But here's what ended up happening. Imagine the electrons can either go through here or they can go through here. They can go through either of those two choices, but they can't go through the wall. That's impossible. So what you would expect if you just allowed the electrons to go through these holes is that you would get, you know, a bright spot right here, right? Those are for the ones coming through here, and a bright spot over here for the ones that are coming through there. So you get 2 bright spots and everything else should be pretty dark. But that's not what they got. What they got when they did this with the electrons is the same thing they got if you use light. And that is, they got a bright spot over here, and they got a bright spot over here, and they got a bright spot over here, and they got a bright spot over here. They got multiple bright spots. So they essentially got what's called an interference pattern. I'm not drawing that very well because I didn't make the spacings very good. Sorry. Essentially what they're getting is a peak and a peak and a peak and a peak and a peak. And that's called a double slit pattern, right? So the same thing happens with light. When you do the same thing with light, essentially what light is able to do, light is a wave, right? So if something's a wave, it can spread out. So essentially the electrons are behaving like a wave and they're spreading out across that entire region of space. So they're actually going through both detectors at the same time, and then they're recombining, the waves recombining to give you this pattern over here, okay? So in order for that to happen, in order to get this pattern here, it could not be the case that the electron's going through either this one or that one. It has to be going through both, like a wave, and then reconstructing itself. So we all know that waves do weird things, right? Waves can bend around corners, right? So like if you're at a building and someone's on the other side of the building and they speak, you can hear them, right? Because the wave is bending around the building, right? So waves can do that kind of thing. Same thing with water. So that means that he was right, de Broglie was right. The electron does, under some circumstances, behave like waves. So the question then is, how does that help us in terms of the atom? And there's actually a very simple answer to that. The way it helps us is that if you consider things like guitars and drums, any stringed instruments or any membrane instruments, actually all musical instruments, including trombones and trumpets and stuff like that. But in particular, we'll use guitars and drums as an example. We know there's vibrations that occur, and we know there's multiples of vibrations, right? We have what's called a fundamental frequency, and then we have what are called overtones, right? And overtones are multiples of the fundamental frequency. So sound is a wave property, right? The reason that we have sound is because we have vibrations of air. It's compression and expansion, but it's essentially a wave. So that means air, when sound, I should say, behaves like a wave. So one of the aspects of that is that you get this idea of specific frequencies, a fundamental frequency, the first overtone, the second overtone. That's quantization. So essentially what you're getting are different levels, different frequencies that have this quantization. And that was known for a long time. That's been known for like a couple hundred years, that the frequencies of a guitar or a drum are quantized. So think about it. If musical instruments are quantized and they are wave properties, and now we say, hey, the electron is a wave property, it should be quantized too, or it might be quantized too. And in fact, it is, right? That line spectrum that we get for the hydrogen atom must be a wave property analogous to what we're seeing with musical instruments, okay? So in a sense, the atom is a vibrating phenomenon. It's like a little musical instrument. It's vibrating, it's constantly vibrating, in the sense that the electron is vibrating around the nucleus. And so that was deBroglie's big contribution to this, is that instead of thinking of the electron as some sort of particle in orbit around the nucleus, it might be more useful to think of it kind of like a drum, a membrane of a drum, right? It's vibrating, it's going back and forth and vibrating across the entire circumference of the drum. And the same thing would be for the electron. It's vibrating in some sense. It's called a standing wave. The wave isn't like moving around like you think of an orbit. It's actually just vibrating in and out. It's three-dimensional, right? So it's not, a drum is two-dimensional, a guitar string is one-dimensional, but the electron would be a three-dimensional vibration. So it's kind of hard to draw it, right? How do you draw a three-dimensional vibration? It's not very easy unless you're a really good artist. But essentially, that was what people concluded based on deBroglie and based on these experiments, right? The double slit experiment was, we use that now, actually, it's called electron diffraction. So you can actually image, right? If you think about it, a microscope, a light microscope uses the wave properties of light to image things that are really small, right? By using lenses and mirrors. But if you use electrical lenses and electrical mirrors, you can do the same thing with electrons. And it turns out that the frequencies and the wavelengths of electrons are such that if you move them at the right speed, you can actually image things that are smaller than you can image with light microscopes, much smaller. So you can actually see, the internal structure of a cell. You can look at these little organelles, and you can even now look at little proteins. You actually see the structure of a protein using this, okay? So that's all a wave-like property of the electron that allows you to use it like you would use light, like a microscope, okay? So what do we have to do in terms of calculations? Very simple, and that is what we do is we use the deBroglie relationship, which says that the wavelength of the electron, so I'll put E for electron just so that we don't get it confused with photons. The wavelength of an electron is h, there's our Planck's constant, over p. So we have a new symbol here. So lambda E is the wavelength of the electron in the atom. Okay, so it has a wavelength, right? Kind of cool. The electron now is this this vibration. Now, what about H? Well, we know what H is, right? H is Planck's constant. (6.626 times 10 to the minus 34 joules times second. So we already know what that is. That's cool. So, you know, this idea that H is in there is interesting too. This H is a fundamental constant of nature. It's a really small value, and we'll talk a little bit more about it when we get to the next topic. But now we got this new symbol called P. And so what is P? P is what we call the linear momentum. Okay, and linear momentum is very simple. It's equal to the mass of something times the speed of something. Okay, I'm not being real technical. Technically, it's velocity. Remember, velocity, direction is important. Speed, it doesn't matter. You're either going 30 miles an hour left or right, but velocity has a directional component. But we're not worried about that. We're just going to do simple calculations here. So this would be the mass of the electron. Right? The electron has a mass of 9.109 times 10 to the minus 31 kilograms. Make sure you use MKS system, kilograms, MKS. And then the speed, well, whatever that speed is, right? So this is the speed of the electron. And it turns out that other particles also have this as well, deBroglie wavelength. So if we were talking about a proton, we would use the mass of a proton. If we were talking about a neutron, we would use the mass of a neutron. But most of the time, as chemists, we're interested in electrons. The electrons are the important particle in chemistry. So for that reason, we just use the mass of the electron. We're talking about the wave-like properties of the electron. In fact, even atoms have wave-like properties, but particularly the smaller atoms, but we're not going to worry ourselves with that. So I'm going to write this as an equation. The momentum is mv, not nu, but v, m times v, mass times velocity, right? And if you take a physics class, you do all kinds of cool calculations with momentum, conservation of momentum, and all of that. We're not going to worry about that. Let me just say that real quickly. Essentially, what we're saying is that the electron does have some sort of momentum. It is behaving as though it's moving, right? And so the amount of momentum that a particle has is equal to the mass of the particle, how massive it is, times how fast it's moving. So you can use momentum in terms of things like a bus, right? A bus has a lot of momentum if it's moving because it has a lot of mass. On the other hand, a little bullet, a tiny little bullet that only weighs a few grams also has a large momentum, not because it has much mass. Bullets actually have almost no mass, but they move very fast. They have very high velocity, so it also has momentum. So again, here's this duality, right? So in a sense, we're saying, hey, it's got a wavelength, but now we're also saying it's got a velocity, it's moving. So it has both, right? So it has what seemingly are contradictory properties. It has a property of a particle moving, but it also has the property of a wave in terms of a wavelength. So the smartest minds in the world have thought about this for many, many years and gotten confused over it. So I won't go too far into it. Okay, so here we go. So that's our little equation there. So I'm going to write the de Broglie equation again as lambda equals h over mv. And there we go. And so that's our equation. So be careful. This is the equation you use for what we call matter waves. So you use this for the electron, use this for a proton. But remember, we also had wavelength is equal to c over frequency, right? That was earlier, right? That's what you use for photons, right? So make sure you're using this one for photons. So if they say, hey, you know, what's the wavelength of, you know, a photon that has this frequency, you're going to use this one on the right. But if they say, hey, an electron is moving at this speed, what's the wavelength? You're going to use this one over here. Okay. All right. So let's take a look at an example. Okay, so Alex has a really fascinating problem where they do this. So let me actually, I'm going to go ahead, I'm going to stop the share here, and then I'm going to show you the screen here because I want to show you this problem. Okay, so share the screen. Here we go. There we go. Okay, so understanding the meaning of a de Broglie wavelength. Imagine an alternate universe where the value of the Planck constant is 6.62607 times 10 to the 11 joules seconds, right? So notice the number 6.626 is the same that we've been using all along, but now they're changing the power of 10. Instead of being minus 34, it's 11. That's a big difference, right? Remember, each number is 10, so it's a lot bigger. So they're saying, hey, you're in some other universe. Like, I mean, there's this theories, right, that we have multi-universes, that there's an infinite number of universes, and we're just in one of them. And in this universe, h is 10 to the minus 34, but in a different universe, h might be 10 to the minus 11. I mean, 10 to the plus 11 might be a completely different value. If that happens, if you change the value of h significantly, what that does is it changes how things behave. So us as individuals, we're large, right? We're not the size of an atom. So that means we behave differently than something that's really, really small, like an atom, right? So we don't behave like waves. We behave like particles. So if you say, hey, I'm a wave and I'm going to walk through this wall because there's an opening, to the side of me, it doesn't work that way. You can't walk through a wall just because there's a door 5 feet away. You're a particle. But if you're a wave and there's a door that's 5 feet away, you can actually walk through the wall because your body will spread out across the room and you'll go right on out and you're fine, right? So waves behave differently than particles. So the question is, in this universe where h is very, very different, would you maybe behave like a wave? So would you behave like what we call a classical particle, which is how we behave, right? Like a ball, a car, an airplane, or a person, or a pencil? Or will you behave like a quantum particle, which would mean, would you behave like a wave? Okay, so here's what they do. They say, hey, you got a raindrop with a mass of 2 milligrams and it's 5.8 millimeters wide and it's moving at 9 meters per second. Is that going to behave classically or is it going to behave quantumly? So in our universe, a raindrop is a classical particle, right? A raindrop is not a wave, it's a particle. And so we would expect in our universe for it to behave classically. Only subatomic particles are going to behave quantumly in our universe. But this is a different value of h. This is 10 to the 11th. So now what you do is you do the calculation. You use de Broglie's formula, h over mv, in order to figure out what you're going to get. Now, what you do in the logic behind this is you look at the size. See how they give you the size? It's 5.8 millimeters. So really what you want to do is you want to look and see when you calculate lambda, if lambda is bigger than the size, so if the wavelength is larger than the size, 5.8 millimeters, it'll be like a wave. It'll be like a quantum. Or if it's about the same size. So if you get somewhere around, 5 millimeters or 6 millimeters, somewhere around that size, it's going to be quantum. But if you get much smaller size than you get, I'm sorry, let me put it this way. If you get a much smaller wavelength, then you get size. So if the wavelength is smaller, significantly smaller than the size, then it's going to behave classically. Okay. So let's take a look here. I'm going to stop the sharing. And then I'll write the numbers down for you. Okay. And you kind of have to go through the logic here. Okay. So let's take a look here. Okay. So here's what they do. They say that H is equal to 6.62607 times 10 to the 11 joule seconds. And then they say, hey, you got a raindrop. So they give you the mass. So this is a raindrop. Okay, so it has a mass of 2 milligrams. It has a size, which is 5.8 millimeters. and then it has a speed, it's moving at, so that's your speed, your V, of 9.0 meters per second, okay? And we just want to know whether it's going to be classical or it's going to be quantum. So here's how you approach it. What you do is you calculate lambda, okay? So calculate lambda. Lambda is h over mv, right? Mass times velocity. However, be careful because as they often do, they give you prefixes, and we don't want prefixes in here. We want to just have it in meters. We're going to make, when you do these, make sure you got MKS. Meters, kilograms, seconds. Seconds is not an issue. They're not going to give you minutes or anything like that, but they might give you the mass not in kilograms, and they might not give you the size in meters. So you want to make sure you've got those. So let's do the little conversions for that. We want to have the mass in kilograms. So if we have 2 milligrams, a milli is 10 to the minus 3. 1 milligram is 1 times 10 to the minus 3 grams. Okay, so what I'm going to do, I'm going to do it 2 steps. 1 kilogram is 1 times 10 to the plus 3 grams. Okay, kilos 1,000. So what I'm going to do is I'm going to multiply this by 1 times 10 to the minus 3 grams is 1 milligram, right? That's going to get rid of your milligrams. That's easy enough. But now I'm just going to write the second one too. I'm going to put kilogram is 1 times 10 to the 3 grams. And that will get rid of the grams. So I'm just going to do those 2 steps in one, okay? So you're multiplying by 10 to the minus 3, and then you're dividing by 10 to the 3. So you get 2.0 times 10 to the minus 6 kilograms. Okay, so there's your kilograms. Okay, now we also have a size in millimeters. So 1 millimeter is 1 times 10 to the minus 3 meters. So let's convert that to 5.8 millimeters times 1 times 10 to the minus 3 meters divided by 1 millimeter. And so you get 5.8 times 10 to the minus 3 meters. Okay, so now we've got that. Okay, so now let's go ahead and calculate. So this is the size in meters. Okay, so now I'm going to calculate lambda. Lambda, but now we're going to use the h they give us. This is not in our universe, it's in a different universe. Okay, so there's your new h. If it was our universe, it'd be 10 to the minus 34, and we would know what we would get for that one. So now we're going to multiply that by the, divide that by the mass. We've got the mass in kilograms, so 2.0 times 10 to the minus 6 kilograms. And then your velocity is not, it's already in meters per second. Okay, so look, let's take a look at the units, joules times seconds. Okay, so the units are going to look kind of quirky here. I'll go over them separately. So 6.62607 times 10 to the 11 divided by 2.0 times 10 to the 6 divided by 9.0. And it looks like you get 36811. That can't be. Oh yeah, that is right. 11.5. Okay, we don't need that many sig figs, but let me show you what the units are. The units are confusing, right? In the numerator, you've got joule seconds. Remember, a joule is a kilogram meters squared per second squared. So that's a joule, but it's joules times seconds. So you put a second in there. Then in the denominator, you've got kilograms and you've got meters per second. So what happens is one of these meters cancels with that meter. The kilogram cancels. One of these seconds cancels with one of those. And then this second cancels with that one. So you're left with meters. Strange, right? Okay. So now here's how we approach this. If lambda is greater than or equal to the size, then it's quantum. If lambda is less than the size, then it's classical. Okay, so essentially, if the wavelength, if it spreads out over a space that's greater than the actual size of the object, then the particle will actually behave like a wave. Okay, so if the wavelength's greater than the size, if they're equal, it will also be. But for the ones they're going to get, they're not going to give you ones that are, you know, oh, it's kind of on the border. They're going to give you ones where it's a big difference. Okay, so the reason they pick 10 to the 11th is because it's such a big number compared to 10 to the minus 34 that almost everything is quantum under those conditions. So if we were in a universe where that were the case, a raindrop would be quantum. Okay, so if wavelength's greater, it's quantum. If the wavelength is smaller than the size, then it's classical. So our answer right here is definitely the raindrop in that universe would be behaving like a wave. It'd be a quantum particle, which it would obey quantum mechanics. It would, you know, completely different physics than a raindrop that we're used to seeing. Okay, so let me show you one more. So another one is an iceberg. That's cool. They give you an iceberg. Again, in the same universe. So it's an iceberg, and the mass, they give you the mass in kilograms. So that's cool. And then they say it's 200 meters wide. And it's moving. Okay, now the one thing they do is they give you the speed in kilometers per hour. Okay, well, you know, I said earlier they're not going to give you minutes, but they gave you hours in this one. Okay, so I was wrong about that. Okay, so again, the question here, is it quantum? Is it classical? Okay, so here's again, I'm just going to get let's get the speed right. Okay, 1.23 kilometers per hour. Okay, so we all know 60 seconds in a minute. We all know 60 minutes in an hour. So that means 60 times 60 is 3,600. So that means in 1 hour, you've got 3,600 seconds, right? So I'm going to say, hey, 1 hour is 3,600 seconds. So that's going to get rid of the hours and put it per second. So that's good. But we still have kilometers, right? Kilos, 1,000. So I'm going to write 1,000 meters per 1 kilometer. And that'll get rid of the kilometer. Okay. I'm going through this quickly, but you can kind of look that over and try it yourself. So 1.23 divided by 3,600 times 1,000, and you get 0.342 meters per second. Remember, we want to have MKS, meters, kilograms, and seconds. So now we've got kilograms, we've got meters, and we've got meters per second, so we're set. So lambda is h over mv. Now we're doing an iceberg. Now, obviously an iceberg in our universe is going to be a classical particle. You do not expect icebergs to move through the earth like a wave does, right? Think about it, like sound waves go through the earth, right? If you have an earthquake here, the other side of the earth will actually, you can measure the waves going through the earth's core, or actually through the earth's crust. I think it goes through the crust and then it goes through the core, whatever. But anyways, those waves can transfer through matter. But an iceberg cannot go through the earth and get to the other side. But if it were a quantum particle, it could. So let's see what happens here. 6.62607 times 10 to the 11 joule seconds. And now we got this big mass. It's 3.8 times 10 to the 8th kilograms. And then our speed is 0.342. It's moving really slow. Meters per second. Yeah, they don't move very fast. Okay. So now we just do that calculation. So 6.62607 times 10 to the 11th. Divide that by 3.8 times 10 to the 8th. Divide that by 0.342. And you get a big number, 5098 And then it comes out to meters, just like we did in the previous example. Okay, so there's your wavelength. The size is 200 meters. Okay, so what did we say before? We said if lambda is greater than or equal to the size, then it's going to behave like a quantum particle. So actually, the wavelength is larger than the size, right? It's longer than the size. So that means that this, you got this big iceberg, which is, well, it's not a real big, some icebergs are bigger than this. So there's a 200-meter iceberg, but the wavelength is like this, right? I'm not even showing the whole wavelength because it's such a big wavelength. It's 5,000. It's like 25 times the size. So what that means is this thing is going to behave like a wave because it's spread out. The wavelength is spread out over such a large region. This thing could actually probably just sort of like, one point be underwater and at one point be above the water. It can actually go through matter and be in different spaces at the same time, just based on being a wave. Okay, so there you go. So in that universe, almost everything ends up being a wave. So there may be some universe out there where H is 10 to the 11th. If so, things like icebergs would behave like waves and you'd have a very different kind of universe. All right. So the main tricky thing there is, the calculation, it's just unit conversions, right? So milli and kilo. But the main trick there is just remember this. If the wavelength is greater or equal than the size, then it's a quantum particle. Okay. So if you do the calculation in our universe as a person, what you get is that a wavelength of a person is around 10 to the minus 30 meters. And the size of a person is around 2 meters. So it's the opposite. In our universe, we behave like a classical particle. Okay. So what we have next to do next week is we'll get into understanding quantum mechanics. So that's section 6.5. which is the Heisenberg uncertainty principle. And then we'll get into the quantum numbers and atomic orbitals. So next week, we should be wrapping all of this up, talking about electron configurations. And really, we're gonna do a little more physics. We're gonna do the Heisenberg uncertainty principle and the quantum numbers, but then we'll bring it back into chemistry. We'll start talking about the elements, the structures of the elements, and then chapter 8 will lead us into chemical bonding. Okay, very good. So, have a great day and reach out to me if you have any questions, and also have a good weekend, okay?
Thank you, Professor. Thank you.
Bye-bye.